last Wednesday we left off talking about this macrozone formation and forged titanium, right, where you had large groups of alpha grains that had similar C-axis orientation, right? So you had these large regions that essentially acted like a single grain, and how new forging processes were developed that put a lot more strain into the material, right? And that really affected the dwell fatigue life quite significantly in these parts. And this dwell fatigue issue is still kind of an ongoing thing, because every so often a part will fail and they'll look at it and it'll have these huge macro zones and no one quite knows why, because it's such a rare event phenomenon now that the new forging processes are in place, right? So in some ways the problem is solved because 99.9% of the parts are fine, but then there's still that 0.1% oddball that pops up. And we really don't know why or where it's coming from. Okay. So I threw this in here because this is interesting, because it points to something that happens quite a lot in material science, that if you develop a new material, it will take 20 years or 25 years before it ever gets used in a car or an airplane or a medical device, but it will be in golf clubs and tennis rackets in 6 months, right? So essentially, things that people will pay a ton of money for a very small benefit for, that doesn't involve a threat to someone's life if it breaks, right? Okay, so beta alloys right, these are alloys that have sufficient beta stabilizers added to them. Excuse me. I sound like a tuberculosis patient. I had the bronchitis, and now I just have this lingering cough, and it has been forever, and it won't go away. Where the alloy is approximately single-phase beta at room temperature. The thing to note is that all beta alloys are really metastable, right? They're low enough that really the material wants to be alpha plus beta, right? And so the term beta alloy is a little confusing because a lot of authors will lump alpha plus beta alloys like Ti-6-4 in with beta. Others will separate out ones that are used only in nearly the beta condition. Right? But in general, I think a good working definition is that if you can cold work it in the soft condition, right, quench it down so it's essentially full beta, have enough beta stabilizers in there to do that, they're typically cold worked and then age hardened to bring out the alpha. That's where I would personally draw the limit between alpha plus beta and beta alloys, right? Just some common alloys. Ti-555 is a fairly commonly used one, right? And this isn't anything new. This is just refresh of the different isomorphous versus eutectoid, and what the different alloying elements do. So there's a couple things we have to really consider when thinking about beta alloy design. The first is that anytime we add eutectoid elements, iron and chromium, we have this issue with solute segregation during solidification, right? And since these elements have a strong effect on the beta transit temperature, if we get segregation, we have an inhomogeneous beta transit, and this leads to a nasty casting defect called beta fleck, right? And this gives us really bad microstructure inhomogeneities in a single part, right? So essentially, to avoid this, there's a whole bunch of different melt practices that are employed. It's not worth going through them, but it means that it makes the cost of processing these alloys quite a bit more, right? On the other hand, adding too many isomorphous beta alloying elements, right, we get a much higher melting point, right? And you can ignore this stuff about master alloying. It's not really a I don't think it's a very useful kind of idea. But here's the issue with beta fleck, right? You can see the great disparity in grain size, right? Grains that are a couple tens of microns to half a millimeter, right? So we get a variation in the beta transits, right? And then where the local microstructure evolution properties is going to be very different. We're going to have local properties. And then if we have cyclic loading, we've got localized high strain localization in these larger grains, and it's going to lead to early crack. All right. And this is just some macro etching that was done to highlight the issue. Highlight the issue of beta fleck. So we talked about all these reactions, right? Beta to beta prime, beta to omega, right? Beta martensite, and beta martensite to alpha, right? So these are all reactions that we sort of talked about, but remember, we're going to be using these beta alloys cold worked, right? So what does cold work mean? Right, we have lots of dislocations, and we're aging to bring out the alpha, right? And so we have to think about all of these different reactions in terms of heterogeneous nucleation, right? Lots of nucleation sites available, right? So, right, especially the omega phase formation, right, can happen in very short aging times when you have a very high dislocation density, right? So this was the beta prime. We talked about how this is very similar to GP zones, and it can either happen by spinodal or homogeneous or heterogeneous nucleation routes. Right, just an example. And so here we have titanium 5553, right? So aluminum, vanadium, molybdenum, chromium with a tiny bit of iron, right? And we can see that the different structures that we get, this is cooling from above the beta transits plus 50 degrees C. Slow furnace cool, we get a very large prior beta grains with a basket weave type structure, right? Air cooling, we essentially retain 100% beta. On the oil quench, right? In this alloy, we'll get an athermal omega fraction, right? And so just the omega as we saw it before, so we get this very fine dispersion of omega in the as quenched condition. Right? Then as we age it, this will coarsen, right? So the oil quench, and then this is 2 hours aging at 350 C, right? So not a very high temperature to coarsen. Right? So if we look at our oil quench and then aging for 4 hours at a higher temperature, right? We see we've got end up with a highly refined distribution of alpha, right? Remember, on the oil quench, we had a athermal omega formed. So what do you think is the likely nucleation sites for this alpha, right? It's going to nucleate heterogeneously on the omega that formed, leading to a very fine alpha dispersion within the beta matrix. Right? This is then oil quenched. If we do the same thing, but then furnace cool, our alpha matures quite a bit, and we develop a very classical basket weave type structure, right? Similar to what we talked about in the alpha plus beta alloys, right? Okay. And then this slide, I believe I actually showed before. Right. Oh, no, it was a different point I wanted to make on this slide. Right. So here, notice in the nucleation of the alpha phase in alpha plus beta alloys versus the beta alloys, right? For similar type of processing, notice we have a large amount of grain boundary alpha, allotropomorphic grain boundary alpha, that we don't have in the prior beta. Here we see a well-developed colony structure with very narrow beta ribs. Right? In the beta alloy, we have this highly defined dispersion of alpha particles of a basket weave like structure. Right? Right? And again, this is what we said before. On fast cool plus aging, we get a uniform distribution of alpha laths, and this is going to nucleate from the athermal omega. Right? Same thing that we had said before. Right? Okay. Right, and no surprise here, right? Heterogeneous nucleation sites increase the precipitation density. This is cold worked in the beta state, right? Oops. All right. So worked and then aged. This is just quenched and aged. And you can see here we have a much finer distribution, right? Right. And we also notice we've minimized the grain boundary alpha formation in the work state, right? This is all because of nucleation sites for omega, which then become preferential nucleation sites for alpha, right? Meaning that the grain boundary is less less favorable nucleation site, all right? And so we can get much higher strength ductility combinations by doing this cold work in the ductile beta state. Okay. This is just the these are not super critical. These are some additional slides from Jim Williams. Note the Comic Sans, right? And so this is just direct nucleation of the alpha phase, right? Depending on some alloys where you don't get as easy omega phase nucleation, you can still heterogeneously nucleate alpha, right? By a direct quench, right? But really, to get a really nice uniform distribution of alpha, we want to nucleate at the beta primer omega sites, right? And that's what he's saying here by single age versus double age, right? So the single age was essentially direct nucleation of alpha at defects. The double age was nucleation of the omega or beta prime, and then aging. So we are working these in this is the beta worked, right? And so that means essentially we're just like in steels with thermomechanical processing, or the no, we didn't talk about any processing like that in aluminum. But in the steels with the controlled rolling or thermomechanical property, we want to maintain the recrystallization kinetics in the beta phase, right? We want we want lots of dislocations, right? So that means we need to slow down our recrystallization kinetics a little bit, right? If we recrystallize too quickly, we're going to recover a nice clean grain structure, right? Either during the deformation or after meta dynamic recrystallization, it's called, right? Where you get the nuclei of the new grains, but then will then grow on the aging treatment. Right? We want to prevent any of that from happening, and so the main knob to turn for that is the molybdenum content in the alloys. Right? So molybdenum becomes quite an important beta stabilizer from that standpoint. Right? Okay. So grain boundary grain boundary alpha we've talked about, right? It's difficult to avoid in all compositions, especially alpha plus beta alloys, right? But you do still see it in beta alloys sometimes, right? And the thing about this is it's quite detrimental to toughness, right? Because this grain boundary alpha now becomes a short circuit fracture path, right? We have long straight regions, right? The crack doesn't have to take a tortuous path through this composite microstructure through the middle of the grain, right? And so, right, again, we want to retard recrystallization, right, and minimize the number of beta grain boundaries as nucleation sites, which again means we need to put enough work in there to get a nice distribution of omega or beta prime or martensitic phases that can then act as nucleation sites. Right. So nothing new here. This is just kind of the same reactions plotted on a TTT diagram, so you can think about cooling rates, right? So beta going to uniform alpha, right? Meaning homogeneous nucleation. That's going to require the slowest cooling rate. It's going to have the slowest kinetics, right? Whereas going heterogeneously, we have enough alpha, right? We can go a little faster, but ideally what we're trying to do is cool through this regime as quickly as possible to get down to this formation of athermal, right? And unfortunately, the nodes, it's tucked back through here, right? So you have to play a lot of tricks with cooling rates and coming through. All right, the other strategy is to come up with multiple step heat treatments, right? And of course, you know, the single step, as we had talked about, again, this is in 5553. All right, we showed that oil quench is definitely fast enough to keep you 100% beta structure, whereas the furnace cool gives you a large basket weave type microstructure. Right. And we want to pay attention to the general properties here. Right? This is going to be low in strength and have reasonable ductility. This is going to be higher in strength, also have a slightly reduced but also decent ductility. Unfortunately, these are in KSI because these came from GE slides. So just pay attention to that. The actual value is not really of concern to me. It's just the general trends. So often these you can get a much wider range of structures by these duplex heat treats, right? And so essentially if you look at this, so you furnace cool and then an age plus oil quench, right? Nice basket weave type structure versus oil quench and then the same type of aging. We have a very fine alpha distribution. And then here we do an oil quench and then a furnace cool, right? And we notice in these two conditions, right, both of these are very brittle. This has the highest strength, right? But the ductility in these is only 2% elongation or so to failure, right? And so this condition where you have good strengths but low ductility led to the invention of these triplex heat treatments, which are kind of the norm now. And you'll notice they're not super successful in the fact that they still generally have pretty poor ductility, right? Where's that poor ductility coming from, right? Essentially, we've got a whole bunch of tiny, tiny little grains here, right? We don't have any easy way for plasticity to occur, right? We've got huge Hall Petch effects, and then these alpha laths, right, all have a huge degree of plastic anisotropy, and they're all pointing in different directions, right? So you somehow need to coordinate deformation in all of these different pointing directions to be able to get any significant amount of plasticity out. But basically, the idea behind these triplex heat treatments is going to be a solutionize, then a oil quench, and then high temp, and then a low temperature aging. right? And depending on how you play with this, you could get different structures, and you'll notice that they don't have recipes up here, right? Why do you think I don't have recipes up here? This is something I want you to think about, right? How you can get these different structures, right? How you can play with the length and the time and the cooling from the different regimes, right? To get these, because these are really good questions to ponder and exam type questions, right? And they're nice open-ended questions because there's potentially more than one processing route you can take to get to here, right? So all you have to think of is a viable one rather than a specific right, wrong answer, right? So it gives me a good way of grading your logic rather than do I know this processing? Okay, just some compositions, right? General properties of beta alloys, right? The big use for these are biomedical applications, right? And so why do we like these for biomedical? The biggest one is it's biocompatible, right? Our body does not attack it as a foreign object, or it encapsulates it, so it just sort of sits there and doesn't worry about it. We don't worry about it anymore. High strength, obviously you don't want things breaking inside. Why is low modulus important? Bone modulus is low, right? Right? What does bone do? Right? Bone is locally smart, right? Bone uses a greedy algorithm when it decides how to restructure, right? Your bone is not a static object, right? It changes in results to the stresses that are put on, right? So now all of a sudden you have a titanium, say, hip implant, right? That titanium is taking up a whole lot of the load. So the bone knows it doesn't need to be as strong there anymore, right? So what does the bone do? It takes away mineralization from that region to put it somewhere else, right? And so now you have the bone growing away from the implant after it's been all healed over a long period of time, right? Not good. So you want to have a modulus that is as close to bone as humanly possible. And there are a whole bunch of medical alloys that can really get the modulus significantly lower than pure titanium, right?